Okay, let's unpack this. Imagine a project that feels like pure summer fun, right? Launching something high into the air in your backyard.
Yeah, classic stuff.
But secretly, it's teaching you some of the most fundamental principles of physics.
Exactly.
Today, we're taking a deep dive into the Humble water rocket, and we're guided by this source, an easy guide to making and launching a small water rocket. And honestly, it reveals surprising depths to this simple toy.
What's truly remarkable here, I think, is how something so accessible, just a plastic bottle, some water, becomes this direct, safe, and incredibly effective tool for exploring core scientific concepts.
Right.
So our mission for this deep dive is really to extract those essential insights, those aha moments from the source, give you a shortcut to understanding the real science behind the splash.
Absolutely. Think of this as your guide to getting, well, really informed about water rockets without having to pore over every single detail yourself. We're going to cover why this particular type of water rocket is just ideal for hands-on learning.
Yeah, the 500 milliliter one specifically.
Exactly. And we'll explore the clever engineering behind its surprisingly simple construction.
It's quite neat.
We'll delve into the core scientific principles at play, like conservation of momentum, Newton's third law, and even some, fascinating atmospheric physics.
The cloud thing is cool.
Totally. We'll also share how you can experiment to get the best results. And finally, connect these backyard rockets to everything from jet engines to squid.
It's a wider world than you'd think.
So let's kick off with just the sheer allure of water rockets. Our source material describes them as eco-friendly and safe, perfect for a summer science experiment.
Definitely. Low cost, high fun.
And what's fascinating is just the number of science questions they pose right away. You instantly discover how changing the amount of water affects flight distance.
Or that little cloud. How does that form inside the rocket after launch? It's quite visible.
Right. And what's particularly cool about the guide we're diving into is that it focuses on making one completely from scratch. No kit needed.
That's right. And it specifically champions the 500 milliliter plastic bottle rocket. It contrasts it with the bigger 1.5 liter versions.
Which you see sometimes.
Yeah, you do. And the insight here is that the 500 milliliter model isn't just smaller. It's like a totally different experience.
Okay.
It's compact, inexpensive, easy to make, and remarkably safe. Yet it's still capable of flying some pretty impressive distances.
Like how far are we talking?
Often over 20 meters, and the guide said sometimes even more than 30 meters.
Wow. That's a serious flight for just a simple bottle. But I'm curious, for anyone tempted to go bigger, what's the fundamental reason the guide really emphasizes the 500 milliliters over the 1.5 liter? Why does going bigger change the safety and practicality so much?
That's a really good question, and it gets right to the heart of the design choices. The 1.5 liter version, well, it can fly higher, sure, but it becomes bulky, and it needs a much larger, completely open space to be safe. Just because it has more energy, a potentially longer trajectory.
Makes sense. More power, more space needed.
Exactly. The 500 milliliter, by contrast, is far lighter, much more manageable. It's ideal for younger builders and just way more convenient for parks or even schoolyards.
Okay.
It hits that sweet spot, Impressive performance without the big safety and logistical hurdles of its larger cousin.
All right, so with that in mind, let's get into the science recipe, what you'll actually need to make one.
The shopping list, basically.
Yeah, and the simplicity is striking. It's primarily 2 500 milliliter plastic bottles. One's the water tank, and the guide is super specific here. It must be a carbonated drink bottle.
Right, for strength. That pressure buildup is no joke.
Exactly. Chosen for its structural integrity. The other bottle gets cleverly repurposed for the fins.
Yeah, you cut it up. And the build process itself, it takes about 50 minutes, according to the guide.
Okay, not too bad.
Not bad at all. And it's surprisingly precise. Each step is designed for both performance and safety.
So it's not just slapping things together.
No, not at all. For instance, creating the head cone and the fin cylinder from the bottles isn't just about cutting. It's about shaping elements that help with the rocket's aerodynamics, its stability.
Ah, yeah.
The guide highlights careful measurement, careful shaping for optimal flight, like flattening the plastic piece, cutting it just right to create fins with a specific gluing tab.
Right.
And it even suggests wrapping vinyl tape around the edges, partly for looks, but also to prevent cuts. Smart.
That is smart.
Similarly, attaching the head to the tank bottle, attaching the fins, it's not just sticking them on.
Yeah.
They mentioned the crucial role of a straw, for example.
A straw, how does that work?
Well, it helps the rocket maintain a stable posture during launch. It guides it along the launch rod, basically. Helps it fly straight and true.
Clever.
And for the air intake, making a hole in a number 6 rubber stopper and putting the inflation needle in these details are all about getting a secure seal and efficient pressure buildup.
Which directly impacts how high it goes.
Exactly. Every little element is an engineering choice, not just a random step.
Okay, now that we've covered the blueprint, which is fascinating in itself, let's talk about the real thrill getting this thing off the ground.
Lift off.
Yeah. Because it's in the launch that all these careful measurements and science principles really come alive, right?
Absolutely.
The basic mechanics seem straightforward. Pour some water in, seal it with the stopper, set it on the launch pad, making sure to thread the rocket straw through the hanger on the pad.
Yep, guide it on.
Then you just pump air into the tank. Now, it's easy to assume, like, more water equals more power, but I'm genuinely curious. The guide mentions the amount of water is key. What surprising insights did the source offer about finding that perfect balance?
Yeah, that's where the physics really shines. If we connect this to the bigger picture, this simple launch opens the door to understanding a really fundamental concept: conservation of momentum.
Okay, explain that a bit.
Well, why do rockets fly? It's because by ejecting mass, in this case, water backward, you create an equal and opposite forward thrust. Newton's third law in action.
Got it. Push water back, rocket goes forward.
Exactly.
Yep.
And to increase the rocket's velocity, you can either increase the mass of water you eject or increase the speed you eject it at.
Okay.
And you're right, the source emphasizes what they call a Goldilocks principle for the water amount. Too little water.
Not enough push.
Right, not enough mass to push out effectively, so your thrust is minimal.
Yeah.
But if there's too much water, some will still be inside at launch, just acting as dead weight.
Ah, weighing it down.
Exactly.
Yeah.
Which also reduces flight distance. So their experimental results show there's an optimal range for the best performance. It's about finding that perfect balance, enough propellant, but not too heavy.
Interesting. So experimentation is key there.
Totally. And they even experimented with launch angles. Theoretically, 45 degrees should give the greatest range if there's no air resistance.
Right. Standard projectile physics.
But their practical tests showed that 60 degrees actually produced the best results.
Huh. Why the difference?
Well, it suggests the actual sweet spot for maximum range is probably between 45 and 50 degrees because of real-world stuff like air resistance.
Which affects things more at shallower angles.
Seems like it. And speaking of stability, they also found that rockets with 4 fins flew the best.
Okay. Why 4?
They were just the most stable in the air, prevented those wobbles that, drain energy from the flight. Keeps it going straight.
Makes sense. And what about that cloud you mentioned earlier? That always struck me as so magical, like a mini weather system in a bottle.
It really is. After launching, you'll often see this small cloud form inside the rocket, making it look white and misty for a second.
Yeah.
This is due to something called adiabatic expansion.
Okay. Adiabatic. What's happening there?
So here's the fascinating insight. You've got highly compressed air inside, right?
Right.
As it rapidly expands and does work, pushing the water out, it uses up its own internal energy.
Okay.
And when it uses that energy, its temperature plummets, like almost instantly.
Wow, it gets cold fast.
Vapor fast.
Right.
And that sudden drop in temperature is what makes the water vapor that's already in the air condense into tiny droplets of visible cloud.
So it's literally creating a cloud because the air cools down so quickly.
Exactly. It's a direct, visible demonstration of thermodynamics happening right inside your rocket. Pretty neat.
That is incredible. Seeing these fundamental principles scale from a backyard toy. It's amazing. But before anyone rushes out to build one, even with something seemingly safe, we absolutely need to talk about safety.
Crucial point, yes.
While this DIY bottle rocket is designed to be quite safe because the stopper just pops off naturally at a certain pressure.
It's like a built-in safety valve.
Right. But it's important to note that some bottle rocket kits can actually be dangerous.
How so?
Well, the issue is that plastic bottles can get invisible cracks over time or from impacts. And under high pressure, those cracks can cause the bottle to, explode.
Yikes. Okay.
So the strong advice is, if you are using a kit-based rocket, you absolutely must prioritize safety by wearing safety goggles during launch.
Protect your eyes.
Absolutely non-negotiable. And related to that, you should also be careful not to raise the internal pressure unnecessarily high, even with the DIY one. What's the limit?
The source recommends launching the rocket at 4 atmospheres of pressure or less.
Okay, 4 atmospheres. What's that like in familiar terms?
It's roughly equivalent to inflating a car tire to about 60 psi, pounds per square inch.
Okay, so that's significant pressure.
It is. It's not a trivial amount of force. So for this purpose, you really should use an air pump that has a pressure gauge Don't just guess.
Right. Measure it. That's a really helpful comparison, putting that pressure into perspective.
It is. And finally, and this is crucial for any launch, kit or DIY, always, always launch the rocket in a wide open area, clear of people.
Definitely. Because while a collision is unlikely to cause a major injury with the 500 milliliter one, it's still potentially dangerous. You don't want it hitting anyone.
Absolutely. Safety first, fun second.
So this whole principle, conservation of momentum, ejecting mass, raises an important question. Where else do we see this at work? It's kind of incredible to think the same physics applies across such a vast range of scales.
It really is. I mean, think about jet engines on airplanes.
Yeah.
Air comes in, gets compressed, mixed with fuel, ignited, and then hot gases shoot out the back at high speed. That's the thrust. Same idea.
Expelling mass backward.
Exactly.
Yeah.
Then you've got nature's version, squid and octopuses. They draw water into their mantle cavity, then forcefully eject it through a funnel.
Jet propulsion.
Underwater jet propulsion.
Yeah.
Propels them forward. And water jet propulsion in boats works similarly, but, mechanically. Uses water instead of air. Lets boats hit speeds up to 90 kilometers sometimes. Even rocket engines for space travel. They carry both fuel and oxygen because there's no air in space.
Right, need their own oxidizer.
Yep, they burn them, eject the hot gas at super high speed. Again, same principle.
And you mentioned ion engines. That sounds really advanced.
Oh yeah, cutting edge stuff. Like on the Hayabusa spacecraft, they use xenon gas, turn it into plasma with microwaves, and then use electric fields to accelerate the ions out.
So it's not a forceful blast?
No, it's very gentle, but it's continuous thrust over a long time. Extremely efficient for deep space missions. But fundamentally,
It's still pushing stuff out the back to go forward.
exactly. From your backyard bottle rocket to deep space probes, it's all conservation of momentum. Mind-blowing, really.
It truly is how that one core idea powers so much. Just circling back to the practical side, for anyone thinking about building these, maybe with a group or for a school project, our guide offers a great time-saving tip.
Ah, yes, the classroom scenario.
Right, because a 50-minute lesson might not be quite enough time for the full plastic fin build.
She's a bit of fiddling.
It does.
Yeah.
So a simply faster way, without sacrificing too much performance, is apparently to use cardstock to make the fins.
Cardstock, like stiff paper.
Yeah, exactly. This can apparently reduce the build time to just 30 minutes.
Oh, that's much quicker.
Yeah, meaning the whole activity, including launching, could probably fit into about an hour.
That's much more manageable for a class.
Definitely. The source notes, they use 2 fins per rocket made this way, just for speed of construction, but you could still do 3 or 4 if stability is more your goal.
Good tip. Flexibility there.
So what does this all mean? Where does this deep dive leave us? You've just heard how a couple of plastic bottles and some water can become this, powerful little classroom for physics.
Yeah, hands-on science.
Showing you conservation of momentum, Newton's laws right there in action, and even how clouds form, literally right before your eyes.
It's pretty direct feedback.
It really reinforces the idea, I think, that truly simple, accessible projects can unlock complex scientific understanding. They provide those really satisfying aha moments that make learning, exciting.
Absolutely. And, considering the versatility of this water rocket principle, propelling everything from a squid to the Hayabusa spacecraft,
Yeah.
it leaves me wondering,
Yeah.
what other seemingly simple everyday actions or phenomena might be demonstrating these profound universal laws of physics, right under our noses, just waiting for us to observe them and really unpack what's going on.